Start?
Yeah, go for it.
Okay. Yeah. Hi, I'm Majd and Rahul and Pratik. We're going to share with you what did we do in the last 1 or 2 weeks working on this project. Right. So we did work on the cosmic web and the brain neural networks. We basically took this paper, the quantitative comparison between the neural network and the cosmic web, which basically just compare the network that's really happening in the outer space with the network that happens basically in our brain. And as you can see in the paper, they said that to a certain degree they found some similarities in the network dynamics, although these things operate at very different physics laws. There's a YouTube video on basically based on our paper. As you can see, they cite our paper here. They start by what Michio Kaku said on the how fascinating is the brain, and then they basically say, but what if I say that it's not only a complex object, but it's basically a replica of the universe itself, and they reference our paper to say that they did find some similarities between the two. This is a YouTube video, you can basically watch it just for the sake of time. We're going to move forward on that. Okay, we can basically just see that at the end. So if you're not familiar with dark matter, basically dark matter is contains basically approximately almost 25% of our universe, and the galaxies that basically are clusters of stars, they mostly contain dark matter. And you can see simulating the dense regions of dark matter is like the cosmic web. That's what we mean with the cosmic web. And dark matter, as research shows, it's collisionless. It interacts only through gravity with basically normal matter. And basically, wherever you have the dense regions of dark matter, you have the galaxies. So saying that cosmic web is the cosmic web of galaxies as well. This is basically what we dealt with. We dealt with FITS files. So FITS files, if you do not know what's a FITS file, it's basically just an image full of pixels, like a matrix, and each pixel has a value, right? So basically, this is just downloading the FITS files from the website of the authors. This is for the cosmic web, this is for the brain cortex, and this is for the cerebellum, okay? This is just using DS9 to view the images. And basically, what I can say, yeah, thank you. So in the pictures or in the FITS files, you have something like this, which is basically the pixels, right? And we put a certain threshold, right? Each pixel is going to have a value. And basically, if that value is above this threshold, you're going to have something like that. A node. Can you just go back one slide? So for example, if you see here, this is a very big node, right? And this is another node, but they're basically, this is one and that's one, but they're just very different size. So basically in our code, we use SciPy and basically to cluster the pixels together. So for example, if this pixel is above the threshold, the value is above the threshold, goes to the next pixel if it's above the threshold, and so on. If all of them are above the threshold, this is considered one node. And basically, for example, if these two pixels are above the threshold, this is considered another node, and so on. So to cluster the pixels together. And after we do that, this is the things that we get of our nodes, which is kind of similar to the original image, which we just downloaded the FITS files there. And I think now I'm going to hand it to Rahul to continue talking about our code.
Yeah. So I'll explain our algorithm, which is MRP algorithm we created. It's basically our initial needs. So what we do after, as Majid said, we get a lot of these nodes, which are cluster of pixels. But we can represent these pixels with only one pixel, which is the centroid pixel. We don't need any other one. So this can be represented, let's say, by this one. This can be represented by this one. So we pick all the nodes and we take one of the centroid pixel, and that is our basically the main node. And what we do is we want to create adjacency metrics. So once we get all the centroid nodes, those are our potential nodes, and we take the size of it. So let's say we have n potential nodes. So our adjacency matrix will be like n squared. So we create an n squared adjacency matrix, and now we know that we can form edges after we have all the nodes and we have an adjacency matrix. So to form the edges, what the paper used is called linking length. So they defined a spatial parameter. So if these are the two nodes, let's say x1 I1 and x2 I2, let's say. So what they do is they calculate the distance between them. They use a different method called halo finding. We use a different method because we have pixels and we have arrays, two-dimensional arrays. So we don't want to do it in lengths. So what we do is if it's 10 units, we convert that to a number of pixels. So let's say we have like 30 pixels. So if two of the coordinates are like less than 30 pixels length, then we mark an edge. And if it's like more than that, then we don't mark an edge. So it's based on a parameter called linking length. And the linking length, the length between the two pixels should be less than that to form an edge. So yeah, can you go back? Yeah. So we kind of calculate two parameters in this. So the first parameter is this one, which is degree centrality. It's basically very simple parameter. So what we do is we calculate the number of edges one node forms divided by the total number of nodes we have minus 1, because we can't have a self edge. We ensure that we don't form a self edge here. So this is our degree centrality. The second is what we also studied is clustering coefficient. We also want to see like how clustered our program is, like how clustered our image is. So what we calculate is the clustering coefficient, which calculates the number of triangles that one node has formed divided by the total number of triangles it can form. So if it's a high value, then it's like localized clusters. Yeah, you can go ahead. So there are two parameters that we actually care about. One is the threshold, as Majd said. So if we want to filter out nodes, we have some threshold value. So the paper has like 10%, takes the top 10% of all the peaks. But for our algorithm, it was like 1.5% for Cosmic Web and 0.2%. So we take the top 0.2% of the nodes, not all the 10% nodes, because it was giving a lot of nodes. So yeah, we can go to the next parameter, which is linking length. So linking length, they mention in like spatial units. So for galaxy cluster, it's like megaparsec, but for cortex and cerebellum, it's like in mu micrometer. So we convert that into pixels using that formulation, and we get like 30, 30, and 15. But the only problem is that the paper also mentions that it's a very arbitrary term. They only take this by their visual inspection. So it's kind of not very well defined, but we take the similar approach and get it in pixels. Yeah, we can go ahead. So yeah, after we did all the things, we get total nodes, and we can compare the total nodes with what is mentioned in the paper. So you can see that for Cosmic Web, we get very good values. We get the same number of nodes that the paper get, like 3800 to 4700. Also, we calculate the average connection. So how much is, if this is the node, so how many nodes are one node connected to. So you can see that it's also in between the range that the paper mentioned. For cortex and cerebellum, we only have like one bits file, so we don't get a range, but we get similar number of nodes and average connections. There is one outlier, but we can kind of ignore that because we tried learning the algorithm multiple times, so we're getting like more number of nodes for Cosmic Web for this A file, and we only have one file of this. So now I can head over to Pratik, and he can explain the results.
So as Rahul and Majd mentioned, we use a different algorithm and different way of selecting nodes and the linking lengths. So on the left hand side, you can see the results from the paper, and the right hand side are from the analysis that we did. We still see like a similar sort of peaks, and now we will see there are also a lot of error peaks as well from the paper, because they have done it on multiple samples. However, we quite are limited on those things. But you can still see like it kind of stopped at 0.5. We still have like a similar sort of peak coming up here. So, and one at the very beginning of it. Typically, we did the same analysis for clustering and the centrality, and especially for the cerebellum data in this one, we can see that there is an extreme high ups and downs going on. However, we don't have that. Now, our intuition and our discussion came up with the potential issues that I will be discussing in the further slides. But just to give you an overview, those also have like a bit of lot of error coming in, which kind of confirms with the conclusions that we came up from the discussions. Now, the main findings from these results were like the networks that we found, the brain and the Cosmic Web, they don't behave like a sorry, I'm butchering the word, random networks, purely because of the metrics that we're getting out of it. We have the clustering values coming from range of 0.1 to 0.4, on an average, and which also defines like they are not random because there's some sort of causal link, which because these are two physical systems which are governed by certain dynamics happening within them. Like cosmic webs are forming, they're clustering because of the gravitational force between them, the gravity that is acting. However, I'm not a biologist, but I guess for neurons it's a biochemical reaction, some sort of, which is potentially making those clusters to form. And also because these are formed by these kind of some sort of causal link, they are very highly correlated and highly clustered, and that is why you don't see a lot of randomness happening. And they are like, because gravity is like is a thing that it's good, it's very strong if it's very close by, but it's not highly effective when it's on a long distance, and that's why you see like these clusters are highly correlated towards or clustered towards the area that they are into, but not to connected well with the ones in the very far distances. Just as a summary, although these are two completely different systems, sort of very high level of magnitude, they still have a self-organization behavior happening. Very complex systems, even though they show some sort of a network which looks sort of similar, because our guess is it is governed by some sort of a causal link. Each of them have a different reasoning for it. Now, and coming to the potential issues and the fixes. So as I mentioned, the cerebellum data had like a bit of peaks coming in. Now, here the way we have selected the nodes and the edges are something that we want to talk about. Like the way we have selected the nodes is looking at the 0.2 percentile, sorry.
I just probably need to.
Oh yeah, sorry, yeah. So it's just because of the 0.2 percentile, which is an arbitrary number to get the same amount of nodes that the author has got, and the linking length is an arbitrary selection process, and that's why these are the potential reasons why the results are not really as similar as it's supposed to be with the author. And if you guys want to find the talk about future work for now, but if you guys want to find the link to our code, it's on GitHub, and we can share it with you guys. Thank you.
Oh, also too, and so at the end of the class today, if everyone can just send me you have the GitHub there, that's great. And if you can send the PyNB file just to my email.
Sure.
Yeah, so you just download that.
Yeah.
So, or whatever you like file you have organized there.
Yeah,
like
sure.
maybe a Python. Okay, great. Okay, any questions? So one of the things, so this is obvious, like this is beyond the scope of the project, but I want to ask, right? So the distance-based definition of links makes sense kind of in the cosmic web network, right? Because you have gravitational interactions.
Yeah.
But neurons don't, they will often connect to their close neighbors in physical proximity, right? But often connect farther away. So how might you deal with that like in the future?
Actually, that's one of the like problems with the author as well. Like he mentioned that, so we can explain like to the image. So if you go to the cerebellum, you can see that there's a lot of long connections. These connections. So we tried getting rid of them, but we can't actually because of the clustering that we do. So we might end up forming more clusters than we should expect, or we might end up getting like ignoring a lot of these long nodes, or they can like merge together. So there are some potential issues that author even mentioned, and we tried getting rid of them, but if we see the results there in cerebellum data, I think, so we can say that there's a lot of like errors that we get. We tried to get rid of them, so we get like no errors here, but I think that's a good point. So for that to be done, I think we need some better analysis for connecting two nodes, and even like filtering out the nodes, so that we can like do more better analysis for degree centrality here that we have done.
So it was also like somewhere when we were selecting the nodes based on the intensity of the image, the matrix that we had. Like from this image itself, we can see the intensity for these connections. I don't know if they're dendrites or not, but they are highlighted as nodes instead of the connection itself. And that is also, I feel, somewhere the reason that the connections that we're supposed to make are not really between the neurons and the neurons itself, but rather the dendrites themselves, or those lines, the connections that are happening, which eventually is resulting into that kind of a problem of not analyzing the image properly. So I guess some sort of an image analysis method would be useful.
And that's right, like for cosmic wave, we didn't find any of these problems. And I think the most similar data we got, clustering coefficient decrease degree, is for cosmic wave. Like that's the best closest we got.
So to the paper.
Yeah.
Yes.
Yeah. So, but for I think cerebellum we got like variations, and cortex was fine because we can see like the cells getting defined here. But for cerebellum we got a bit different result because it will depend on how you do perform the image analysis and then pick up the linking.
Great. Yeah. Okay. Okay. Thanks. That's great. Who wants to go next? Yeah, go for it. And so I feel a little skeptical about the connection between the two because there's a lot of things that obviously that's beyond the scope of like the paper and replicating, right? I feel a little, like because of the differences in the scale. It's it's an interesting idea, but it would take a lot to make that comparison.
Yeah. Actually, one of the slides that I kind of skipped was on spider webs. So you know, like on the windows, you see like a lot of spider webs and stuff. Not of this one, apparently.
Yeah.
But they also have like dust particles connected, which potentially could be also like a network that can be analyzed. Which, yeah, might be because of some sort of
So this
physical
kind of approach can be used for
translationally in that
comparing two.
Yeah, any two physical systems.
Yeah.
Yeah, there's a great kind of discussion about, this is not actually networks per se, actually it is in fact. There's a great discussion about river deltas, like river beds, and tree arborizations in the air, so the branches, and they actually get a very rigorously defined comparison there, very well controlled, and they show that the river branching and the tree branching actually follows a similar network process. Yeah. So there's some, like, there are ways to actually do this really nicely. That's an interesting reach, but yeah, it's interesting. Thanks.
Yeah.
Please.
Yeah, so the paper I'm doing is this